this series we are discussing the quantum devices. Last time we have discussed the two quantum devices, one is QUAD and second we are in that continuation we are discussing the quantum cascade laser. That we have discussed that quantum cascade laser is different from the conventional laser. So, if we are talking about a more complex gas molecule that absorbs at the longer wavelength and the greater measurement, then it is possible just to use the QCL, quantum cascade laser based system than the current technology, right. QCL allows for remote sensing of these complex molecules, whereas most traditional methods require a sample of a subject material. So, some technical challenges remains before these systems are commercially viable on the large scale, but the technology is advancing rapidly. So, we are discussing the behavior and the working of the quantum cascade laser. So, strongly simplified schematic diagram as we are having on the screen. This schematic is define the gain region of the quantum cascade laser. So, this diagram shows the quantum cascade laser electron energy level versus the position in the structure. So, which contains the quantum wells. You are seeing here that there is a periodic quantum well in this electronic structure. Now, you are seeing the three arrows here, one is in the blue, second is in the red and third in the grey color. Now, these defined the variation of the waves function. So, now the overall downward trend of the energy towards the right hand side is caused by an applied electric field. Means when we are applying the electric field, it means what we are giving this to raise the atom from lower to higher level, we are using the electric field for the pumping process. In reality, each gain region must be divided into the active region and an injector. Why injector? Because the signal is going from one well to the another for the further processing. Now, this figure illustrates what happened to an electron injected into the gain region and then what is going inside a periodic structure and then finally how it is supplying the population or the electron or give the wave function to the another potential well. So, now the electron is injected into the upper sub level mini band in the active region and undergoes a radiative transition that is defined by the blue arrow. Now, you see there is a transition arrow when the electrons is injected, that is from the left hand side you can see through the arrow which is the grey color, then the upper sub band, it is this the electron injected at the upper sub band and from the upper sub band it is going to the lower sub band. So, it is undergo the radiative transition that defined in the blue color. Radiative transitions means it gives the laser action. Now, to the lower sub levels, this is the laser transition on which stimulated emission occur. Basically, this blue color transition, this blue color, the arrow which representing the transition from upper level to the lower level and that produces the lasing action. Now, at this sub level, then it fastly here is relaxed and then it just go to the another sub level and that is the fast non-radiative transition that defined by the red arrow, typically by the photon emission to the lowest sub level of the period. From upper level to the lower level, from then lower level to the ground level, it just transfer its electron. So, the transition from the upper level which is represented in the blue arrow is the lasing action and it is radiative, but in the red color it is representing the non-radiative transition, there it relax and go to the lower sub level. Now, the third one, now you see it is very clear, it then tunnels through a barrier into the upper laser level of the next period, that is defined by the gray arrow. You can see there is a arrow between the two tunnels or the two this arrow represent that there is a tunneling takes place through the barrier into the upper laser level of the next period and in the neighboring quantum well. It means it is transferring the number of electrons to the another level of the another periodic potential. So, now you here, because the sequence is repeated in every period, so a single electron can generate in ideal case of the perfect quantum efficiency, one photon in each active region is transferred, as using the several tens or the even about 100 such period in the series a cascade we can have, therefore yield high optical gain and multiple photons per injected electrons at the expenses of the comparatively high required electrical voltage. So, operation voltage of the order of 10 to the 10 volt are common in this series, whereas only a few volts are sufficient for the ordinary laser diode. Since the transition energies are determined not by fixed bulk material properties but by designed layered thickness and composition of the quantum well and the barrier. It means that the functioning of this cascade laser basically depend upon the property of the layers or the thickness of the layer and layer thickness and the composition of the material through which we just preparing the material, quantum well or the barrier. Quantum cascade laser can be engineered for operating the wavelength ranging from the few micrometer to the well about 10 micrometer and even into the terahertz region. The quantum well structure is embedded in a waveguide that confines the optical mode and form the part of laser resonator. So, these wells are work as a laser resonator and the resonator is often of the DFB or DBR type and that obtain the single mode operation. There are also the external cavity implementations where a wavelength tuning element such as diffraction grating is placed outside the chip or a part of the resonator. Means whenever we just require the tunable laser, then the impurity may be added in the composition. So, what are the typical properties of the quantum cascade laser? As we know, in the laser the important is the output wavelength. So, what is the output wavelength of this laser? That is the main important part. So, there are some properties of the quantum cascade laser. Most quantum cascade laser emit mid-infrared light, that is the wavelength between the 3 micrometer to 50 micrometer according to the survey, and are therefore a type of mid-infrared laser sources. So, output of the quantum cascade laser is in the mid-infrared laser sources. So, however, quantum cascade laser can also be engineered to generate the terahertz wavelength. Means we can have the terahertz wavelength output in this quantum cascade laser that provide particularly the compact electrically pumped sources of the terahertz radiations. Even the room temperature terahertz emission is possible via internal difference frequency generation. And what about the output power and efficiency of QCL laser? This is continuously operating at the room temperature. Devices typically reach the multi-watt level output power. Through the watt level continuous power has been achieved in the specific designs. So, with the liquid nitrogen cooling, multiple watts of the continuous output are readily attainable. So, at room temperature what level peak power are also possible when short electrical pulse are used. At the short electrical, the output power we can get. The power conversion efficiency of the QCL is usually on the order of the few tens of percent. So, recently devices with the efficiencies around 50% have been demonstrated, although these values have so far been achieved by only under the cryogenic operating conditions. Another properties is the dynamic properties. What are these dynamic properties? Where we are having a relaxation oscillations. So, carrier lifetime in the quantum cascade laser are much shorter than that of the conventional interband laser diodes. So, carrier lifetime is much smaller as compared to the other diode lasers. So, these lifetime are mainly limited by rapid phonon assisted scattering processes. So, as a consequences, QCL exhibit heavily damped relaxation oscillations. Their transient dynamics are typically over damped. After some time, it is just damped. So, this in turn enables very high intrinsic modulation bandwidth, often in the range of several tens of gigahertz. Another point, another property, dynamic property is the line width. The emission of line width of the QCL is usually quite small, which is highly advantageous for the many kind of spectroscopy. Line width is very small, so we are having a good output. So, one reason for this is very small line width enhancement factor characteristics of the inter-subband gain media. So, another property, dynamic property is the mode locked operation. Quantum cascade laser can also operate in a mode locked regime. So, although achieving the stable pulse formation is considerably more challenging than in the conventional interband semiconductor laser. So, there is a possible in the quantum cascade laser. So, the main difficulty for the passive mode locking arises from the ultra fast carrier dynamics in the QCL with extremely short upper state lifetime. So, despite these challenges, several approaches to mode lock operation have been demonstrated. First is the active mode locking. What is this active locking? By applying an external radio frequency modulation, usually through a integrated electro-optic or the acousto-optic modulation, QCL can produce trains of ultra short pulses. So, this method does not rely on the slow saturable absorptions and is therefore compatible with the fast gain dynamics of the QCL. So, there is a ultra short pulses that produce the active mode locking. Another is the hybrid active and passive scheme that define the devices incorporating the engineered saturable absorptions or sections with non-linear losses having the shown signatures of passive pulse shaping when combined the active modulation. So, these are the hybrid active and passive scheme. Another is the frequency comb operation. So, even when not producing the isolated short pulses in the time domain, QCL can operate as a optical frequency combs. In such cases, the phases of many longitudinal mode becomes the locked through non-linear processes such as a 4-wave mixing within the active region. So, QCL frequency combs are especially promising for broadband mid-infrared spectroscopy and dual comb technology. So, fully passive and passive mode locking without external modulation remains experimentally difficult. So, largely due to the rapid gain dynamics and limited dispersions control. Nevertheless, ongoing advances in the dispersion engineering, heterogeneous integration and low loss wavelength design continue to bring more robust mod lock performance within the reach, especially for the application requiring the compact pulsed mid infrared or terahertz sources. So, we require the we are having the compact pulse mid infrared output and the terahertz output. So, what are the application of the quantum cascade laser? This laser, as we are talking about the nowadays the quantum computing and the advancement in the technology. So, where we can use this quantum cascade laser. So, most important application of this laser is in the laser absorption spectroscopy of trace gases. For example, if we take the detecting the extremely low concentration of the pollutants in the air. So, and moreover, because offering the suitable wavelength for many molecular absorbers. So, we have QCL combines narrow line width with only tunability. So, we can have the narrow line width and the absorption. In the absorption spectroscopy, it is very sensitive just to get the wavelength which is very less, and that is used in the just in the detecting extremely low concentration of pollutant in the air, that making idea sources for the precision spectroscopy. So, we are having a line width and the good tunability. Because of that, it can be used to detect the gas molecules which is at the having the very low wavelength. So, terahertz QCL are also attractive for the various imaging techniques. So, we are having the terahertz radiation also that can be detected. Another application area of terahertz QCL is the free space optical communication. So, although terahertz beams exhibit sustainability higher beam divergence than the optical beam, directed transmission over the short distance in the air is feasible. So, free space optical communication is possible through this QCL. A notable military application is their use in the infrared countermeasures, and where the mid infrared QCL disrupt the sensors of heat seeking missiles by directing tailored infrared radiations at them. So, there are the various application of QCL. So, where our QCL are used? We can used in the gas sensing measurement system, and moreover the system based on widely tunable. QCL can be used to measure the multiple gas species, and narrowing the targeting systems can detect it, and moreover the measure the gas concentration in the parts per trillions range, not a millions but in a trillions range we can measure the gas concentration. So, QCL used for the gas sensing. And moreover this QCL, this is distributed feedback QCL, and which is capable for the wavelength tuning up to the few tens of the centimeter inverse. External cavity we can use is as a expand of the tuning range of the quantum cascade laser, that must be 1000 centimeter inverse. So, it is used for the sensing and measuring multiple gas species as per demand, as per the sensitivity. So, because they require the relatively low power and are very small, moreover low electric power, and QCl based system replace larger and slower FTR mass spectroscopy systems, and these are having the application, just these are more sensitive gas detection as compared to the other machines, other electrical appliances. So, specific example of the application of the QCl, as we have discussing that it can absorb the gas, and moreover mode of compound that absorb in the terahertz range, means this QCl work in the terahertz range, that is the biggest application of this QCl. Moreover, real time monitoring is possible because it can detect the pollutant in the air at the real time, and moreover remote sensing of the industrial exhaust, and that sticks for the environmental regulation enforcement. Moreover, it is a compact and fast airborne instruments for monitoring and measuring the trace atmospheric gases in the studies related to the global climate changes. So, at present QCl are still somewhat specialized device. Manufacturing is difficult to optimize, and small batch sizes result in a high unit cost, because here we are using the, just we have to create the potential well, quantum well for this, and moreover their doping and the compositions are important. As the value of these devices is more widely realized and more applications are created, so QCl will become more readily available and affordable as per the application. So, if we talk about the band structure of QCl, so the quantum cascade laser is based upon the inter subband electron transition inside a quantum well structure. So we are having that there is no longer limited by inherent band gap, and can demonstrate a very versatile source using one material system, that we have discussed, that it is having a various potential well. You can see here there is an injector and the active region where we are getting the output. The blue sign is representing that this is a lasing action can be produced between these sub levels. So, tunability we can get through this through this quantum cascade laser. So, tunable emission over a wide spectral range is possible through the range is 3.7 to 16 micrometer. At the room temperature it is possible. So, up to now we have discussed the quantum cascade laser and how it works and what are its applications. Next we will discuss the another quantum device. Thank you very much.